Imagine a world where machines could not distinguish a cat from a car. Yet today, AI can see, recognize, and interpret images with astonishing accuracy thanks to a hidden journey of computer vision. In this video we'll trace that story, starting with the first edge-detecting algorithms that turned raw pixels into meaningful lines, then explore how feature-based methods gave computers a way to spot patterns, before diving into the deep learning revolution that powered CNNs and broke ImageNet records. We'll look at modern vision systems that mimic human perception and glimpse what's coming next. If you want to keep uncovering the secrets behind AI's sight, hit subscribe and join the adventure. From the moment a camera shutter clicks, the world is reduced to a grid of numbers, brightness values arranged in rows and columns. Early computer vision scientists asked a simple question: how can a machine make sense of this sea of pixels without understanding what it's looking at? Their answer lay in mathematics that had been around for centuries, repurposed for a new kind of sight. By sliding small, carefully weighted grids, called kernels, over the image, they could highlight sudden changes in intensity that reveal where one surface ends and another begins. The Sobel operator, with its pair of perpendicular masks, approximates the gradient, turning subtle shifts into bold lines that trace edges. Building on that, the Kenny edge detector added a cascade of steps, smoothing to suppress noise, finding the gradient magnitude and direction, then thinning those ridges to single pixel width and finally linking them with hysteresis thresholds to keep only the strongest, most continuous boundaries. These algorithms transformed raw pixel data into crisp, interpretable sketches of shape, laying the conceptual foundation for every later breakthrough, from feature descriptors to deep learning convolutional nets. Yet, as powerful as they are, handcrafted filters hit a ceiling when scenes grow complex, lighting shifts, or objects overlap. The next leap would require letting machines learn their own filters from data, a shift that would redefine what it means for a computer to see. But the early days of simple pixel matching were like trying to read a book by staring at individual dots of ink. It wasn't enough to know that a pixel was red or blue, the machine needed to understand structure. This realization sparked the era of feature-based methods. Instead of looking at the whole image, scientists taught computers to hunt for landmarks. Think of these as the digital fingerprints of an object. They looked for sharp edges, distinct corners, and unique blobs of contrast. This was the birth of algorithms like SIFT and HOG, which acted as a set of mathematical goggles, filtering out the noise to find the essence of a shape. Suddenly, a computer didn't just see a grid of numbers, it saw the curve of a jawline or the straight edge of a skyscraper. It was a massive leap forward, allowing machines to recognize objects even if they were tilted, zoomed in, or partially hidden in shadow. For years, this was the gold standard. Engineers spent decades meticulously handcrafting these features, essentially telling the computer exactly what to look for. It was a triumph of human intuition, but it had a fatal flaw. We were still the ones doing the heavy lifting, defining the rules of sight. The real breakthrough would come when we stopped telling the machine what to see, and instead, taught it how to learn for itself. Before the deep learning boom, machines could recognize shapes only when programmers painstakingly told them what to look for. Then, in 2012, a quiet revolution ignited on the ImageNet benchmark. A team led by Alex Krashevsky, Ilya Sutskever, and Geoffrey Hinton unveiled a convolutional neural network they called AlexNet. Unlike earlier models, AlexNet learned its own filters directly from raw pixels, stacking tiny, overlapping receptive fields that responded to edges, textures, and eventually complex object parts. Trained on over 1 million labeled images and powered by GPUs, it slashed the error rate from 26% to just 15%, a leap that stunned the computer vision community. The secret lay in the convolution operation. By sliding small kernels across an image, the network shared weights, dramatically reducing parameters while preserving spatial hierarchy. This weight sharing let deeper networks extract ever more abstract features without exploding in size. As researchers piled on layers, added dropout, and refined activation functions, performance kept climbing, turning ImageNet from a benchmark into a proving ground for the next generation of AI vision. The ripple effect was immediate. Startups, tech giants, and labs rushed to adopt CNNs, setting the stage for real-time object detection, facial recognition, and the immersive experiences we take for granted today. And now, with foundations laid, the next frontier asks how machines can not only see but understand the story behind every pixel. From the early days of handcrafted filters to the deep convolutional nets that sparked the first computer vision renaissance, the field has been on a relentless quest to mimic the way humans perceive the world. Today, that quest has taken a new turn with transformer-based architectures, the same models that revolutionized language, now reshaping how machines see. By treating image patches as sequences and letting self-attention weigh their relationships across the entire frame, vision transformers capture long-range context that convolutions often miss, leading to breakthroughs in accuracy and robustness. These models power real-time systems that can spot a pedestrian stepping off a curb, guide a drone through cluttered forests, or flag anomalies in a medical scan within milliseconds, all while running on edge hardware that fits in a palm. Yet as the technology spreads, so do the questions it raises. Who decides what a surveillance camera should notice, and how do we guard against bias that can amplify existing inequalities? Researchers are now weaving fairness checks into training loops, demanding transparency in model decisions, and exploring ways to let vision systems explain what they see in human understandable terms. The next frontier isn't just better performance, it's vision that is both powerful and principled, setting the stage for AI that doesn't just see, but understands responsibly. As we look ahead, the promise of vision that learns from fewer examples and adapts on the fly hints at a future where machines could assist artists, scientists, and everyday creators in ways we have only begun to imagine. In short, AI's journey to seeing the world shows how mimicking the human brain's visual cortex with deep networks turned raw pixels into meaningful understanding, revolutionizing everything from medical scans to self-driving cars. If you enjoyed uncovering this hidden story, smash the like button, hit subscribe for more deep dives into tech breakthroughs, and drop a comment telling us which application of computer vision excites you most and why. Your thoughts help shape future videos, so be specific and share any projects you've worked on or dream about building with Vision AI.